This is chapter 6.4, DFT. The word DFT stands for discrete Fourier transform. We'll first discuss why we need another transform, show the analysis and synthesis equation, as well as relating DTFS to DFT. In 6.4.2, we then use the DFT and introduce circular shift and circular convolution and how we overcome circular convolution by zero padding. Now, why another discrete time Fourier transform? The big idea is this. Typically, we are given a big, very long waveform, and if we want to Fourier transform this, then we can take the discrete time Fourier transform. But when we do that and taking a very long window of signal, then our Fourier transform will tell us information of this whole long window, and that's not what we want. For example, if we only want to zoom into a very small part like this, and we want to study its characteristics, its distribution of frequencies, then basically we only should take a small window of this, maybe 256 samples, 512 samples, and extract it out. For example, like this. And once we have extracted it out, then of course we can take discrete time Fourier transform, because this is aperiodic. It has finite support, but it doesn't repeat. But when you do that, you realize that you are trying to take x of omega, and omega is continuous from 0 to 2 pi. And that is not computationally feasible as well. The only computational feasible approach is to do DTFS. So what does DTFS do? Well, first is we repeat the signal, and now it's a periodic sequence, and we can, since it's a periodic sequence, we can take DTFS. So the solution is, when we have a finite sequence, we pretend that it is periodic, basically extend it to be periodic, and then take the DTFS. And whatever we actually extract the information, we have to remember that the real underlying data is actually only a single period. So this is what we're talking about. We have this very long sequence, and we are going to take only these 5 samples, for example. And in fact, these 5 samples look like these 5 samples, which is the DTFT, which is an aperiodic sequence. And in fact, this 5 sample is also like these 5 samples, which is the single period of a periodic sequence, repeating every 5 times. So when we take a very long signal and we take examine only 5 samples of this in this example, we are actually behaving as if we are doing, later on when you see the equation, we are pretending it to be periodic. And that is what DFT is. So in the analysis equation of DFT, you realize that this particular equation here is exactly the same as here. So look, from n equals to 0 to n minus 1, the signal itself, the single period, e minus j2 pi n times kn. Look, n equals to 0 to n minus 1, that 5 samples in this example, e minus j2 pi over n kn. So this guy and this guy are exactly the same. They will give you the same answer when these 5 samples and these 5 samples are the same. What's the difference? That 1 over n here. 1 over n is in front of the ck, and there's no 1 over n here. And there must be some symmetry. So you realize that the 1 over n happens here, and there's no 1 over n here. So this confuses a lot of students. You have to memorize all these equations by heart and understand that in this case, DFT, the representation is identical to the DTFS representation, except for the change of scaling. One is the analysis and the other one is at the synthesis. But other than that, they are actually totally the same. So let me repeat that. DFT and DTFS are almost the same operation to convert a sequence of signal into its frequency representation. The only difference is In DTFS, 1 over n is here. There's no 1 over n for the DFT in the analysis equation. But if we then replace, and if we calculate this ck, then we can say xk equals to nck, therefore implying that ck equals to 1 over n xk. Right? So that's the idea. Always remember that the small x represents the time and the big X represents the frequency. So this is the final take-home message. When we perform inverse DFT of xk, we'll get xn. But remember that this xn is only valid for the n sample. Outside this range, they are not valid. This is opposite to this. Ck is from a periodic signal, the frequency representation of the periodic signal. When we get xn, this is still periodic, as in the real data. Here, when we take xk, the frequency representation, and we do inverse DFT, we'll get xn, but only the 5 samples here are correct. Outside here, if you try to use this equation, you'll still be periodic, but they are not representing the real data. This is what this warning is about. And maybe I draw for you another diagram to show this. The original sequence is this. I've windowed it. I've only taken n samples. Outside, because I've windowed it, I do not know what's happening. I perform the DFT. What do I get here? I get xk here. And once I get xk, I can perform inverse DFT. And then what do I get? In fact, I get x, then with a little tilde on top to say that it is repeating, because this is exactly the inverse DTFS representation, right? Now, so what happened now? In fact, only this is the same. This is repeating if we want to calculate different n, but we actually have no idea what these were. So this is what we are saying, that these are invalid values even though we can calculate it. And because they are invalid values, it will cause us 2 problems that we need to solve later on. One is called the circular shift, and one is called the circular convolution. We'll study this in the next slides. Thank you.